All right. Good morning, good afternoon, good evening, everyone. Welcome to day three of week 0 of the summer school. Today, it's a pleasure to have Carlos Zapata have come here to talk to us about higher-arity mathematics. Carlos has been a fellow of the Wolfram Institute, for those of you who are following the activities at the Institute. He's originally a mathematical physicist working on both math physics on both sides of the aisle. And he has been working, well, he's originally done his studies in Spain and then his PhD from the University of Edinburgh. More recently, Carlos has been a founder and president of the Society for Multidisciplinary Sciences. And in that context, you may have a look at some of the activities he's holding over there, all kinds of interesting workshops. More importantly and interestingly, Carlos has been working a lot on this project, Higher-Arity Mathematics. And with Nick Merzen, who you already have met, Nick and Carlos have also developed a hypergraph tacklet for Wolfram Mathematica, where you can do higher-arity and hypergraph algebra calculations, both visually, symbolically, and in all ways. So it's a great tool for mathematical and computational purposes. And today, Carlos is going to give us a glimpse into this world of higher-arity math, where by higher-arity, we mean things beyond binarity. So thank you, Carlos, for being here, and we are looking forward to a great talk.
Well, thanks for the very detailed and kind introduction, Xerxes. It's always a pleasure to come back to this particular forum. Due to logistical reasons, I can't be on site for the summer school this year, but hopefully this contribution will give some ideas for people to use over during the events of the Wolfram Summer School. So this talk is particularly happy for me, or it marks a moment of pointed joy for me personally, because we are going to be developing a project over the next few years at the Institute on these topics and related themes in the physics project and in the whole Wolfram endeavor. So in the past, when I talked about this topic, I always I was unsure how much more progress we were going to make. And as I will get to in the end, there are many open questions. It is a very open-ended research program. And so it was a little bit bittersweet to get to these talks, because there are very juicy scientific bits, and it was never sure how much opportunity we'll have to explore them. And now we actually know that we're going to be exploring this for at least a couple of years. So hopefully a lot of results to come soon. So stay tuned in the future, either on the Wolfram Institute outlets or future events. And my personal work for more updates, because hopefully they will be happening. So what are the updates about? So what is the topic? So I will share here my presentation. Let me know if the size is okay. Is that reasonable?
Sounds good.
Solution. Okay. So move you guys' faces over here, so I have some insight on who's virtually with us. And yeah, so yeah, I titled this talk Charting the Outer Reaches of the Algebraic Universe with Hypergraphs. I mean, of course, perhaps unnecessarily poetic, but that's sort of the spirit of, by the way, if you see me looking to the side, that's where your faces are, so it might be kind of like looking back and forth. So I wanted to motivate a little bit. Some of you obviously know about this already. You've heard my talks before, but I wanted to motivate a little bit what I experienced as being stung by the ternary bug. And I coined this phrase because it's not just me that have experienced this. I've heard reports from at least 6 or 7 physicists and mathematicians, particularly quite veteran ones. So people are already retired at the end of their careers and are already professors in universities, who describe similar occurrences. So basically, you are working as a mathematical physicist or as a geometer or as an algebraist, and at some point you realize wait, there seems to be a lack of higher-arity operations. So arity just means the number of arguments that you put into an operation. So typically, if you come from primary school, you do addition or multiplication, you're usually putting two numbers together and doing something to them, right? Or maybe in Boolean logic, right? Like you have truth values and or other Boolean operators. Those are very typically binary. And when you learn a little bit of mathematics, you realize that formally speaking, arity is not there aren't any boundaries to arity, right? Like you could have multi-arity operations, and in principle, you could develop models and entire theories out of this higher-arity operations. And so you get a bit mystified thinking, hey, why aren't there so many, just ternary operations maybe lying around? So I put ternary as a sort of stand-in for higher than 2 arity. And of course, it so happens that ternary itself is quite unknown. I would say ternary is more unknown than quaternary because many times you can make some kind of a square of binary arguments in quaternary. But anyway, so you come to realize, wait, why don't we have more ternary operations lying around, and why aren't our theories richer in higher order or higher arity operations? And the dissatisfaction comes when you actually try to search for answers and you don't find many. You just find a lack. At first you begin as thinking, this might be my own ignorance, and if you're a humble intellectual, as you should be, you are always kind of like going after papers and books and so on. And then you realize that there is a hell of a lot of literature on n-array operations, that is algebra that is generic in arity, and that could, people don't really care about the number of arguments in their operations. They just know that they can deal with arbitrary numbers of arguments. But then you realize that if you try to drill down on specifics about ternary operations, like you have for binary operations, you have, a lot of books on groups, a lot of books on monoids, a lot of groups and books on semi-rings and all kinds of, composite versions of these. But you don't find similar books on ternary groups or, something as I might mention later called semi-heaps, which are some sort of related cousin to semi-groups. And so you basically begin as a kind of a humble intellectual saying, this is just my ignorance, but then you actually realize that there's a lack of literature. It's not just your perception, there's an actual lack of this. And so there is something going on. And so my expectation today is I want to give you a glimpse at a way to understand higher-arity operations in a very specific way using hypergraph rewrite systems. Of course, you are in Wolfram Summer School, so you should be hearing about hypergraph rewriting in some capacity every now and then. So this is your daily dose of hypergraph rewriting. Now in the form of how do you approach these higher-arity operations? So as Xerxes just mentioned, this can be very interactive. This is a notebook that I can share and you can have. And please feel free to pause me and ask me any questions. I do have a kind of script that I want to follow to walk you through the basic ideas. And this code is practical, so you can actually copy it and run it yourself and do some experiments. So for those of you in the audience that have some mathematical knowledge and or physics knowledge, you might be familiar with Lie algebras, and arguably Lie algebras are one of the most important mathematical or algebraic objects for modern physics. Most of the success of modern particle physics, and to a degree also general relativity, is due to knowledge in Lie algebras and development in Lie algebras and adjacent topics. So there's one very clear problem that can be formulated in terms of Lie algebra. So I'll mention this in a couple of minutes. If someone is curious about it, I can drill down further. Otherwise, it's just historically what got me into these topics to begin with. I'm not going to talk about this in this talk. I'm not going to press further on this particular issue of 3 Lie algebras, but I wanted to mention it because it's how I got into this now about 3-4 years ago, and that's what prompted me basically this was the moment the ternary back stung me, right? So a 3 Lie algebra is very much like an ordinary binary Lie algebra, right? Lie algebra, has a bracket and has some specific behavior that we call, being antisymmetric and being Jacobi or satisfying the Jacobi identity. So it turns out that this notion you can extend very easily to higher-arity brackets. And if you consider a ternary bracket, so you operate 3 elements of your algebra instead of 2, you can write down a condition for antisymmetry that is very similar, right? You can just move your arguments around, and every time you perform some permutation of arguments, you pick up a sign according to the signature of your permutation, right? That's quite easy. But what is not so easy to generalize, but turns out to be actually very feasible and very natural, is the notion of a Jacobi identity. Right? I'm sure that many of you are familiar with the Jacobi identity as something like, you take double bracket and you cycle the elements inside and you get 0. But the best way to understand the Jacobi identity is to think of the bracket as acting on itself, right? So the way you should understand this left-hand side over here is that you have the bracket x, y, something. And then what you put for the something argument, which is the third argument of the bracket, you insert another full bracket of a generic arguments A, B, C. So the formula that is written on the right-hand side, if you look closely, all it does is it takes the bracket X, Y, something, and it plugs it into A, B, and C, right? It just goes through and it goes, A, B, and C, and then you distribute. That formula, if I were to simply call the bracket X, Y, something D, for example, I could simply write as, I am applying D to A, B, C. And then suddenly what you get on the right-hand side is D of A, C plus A, D, B, and C plus A, B, D of C. So if anyone has minimum experience with calculus, you should be thinking, aha, that's like a derivative, that I have a product of 3 things, and my derivative goes through and operates like the product rule. So that's exactly what it is. We call this an internal derivation of the bracket in a bit more algebraic terms. But so the reason I'm telling you this story is that this particular axiom, this particular formula, what we could call the ternary Leibniz identity, sometimes also called the Filipov identity, is extremely natural, right? You don't have to know any further mathematics to say, well, if you had it for the binary case, I can do it for n-ary case, because it's just applying the product rule of derivatives. So, and there's in fact a very natural example of this kind of algebras. I mean, the first thing you do when you define an algebra is to say, can I find any non-trivial examples? And yes, there's a very natural non-trivial example. And for this, I'm going to walk you through a case of revisiting the structures that you're very familiar with from high school or even earlier, and do a little bit of a mental exercise. So does everyone remember the cross product formula from high school, right? When you have basically two vectors and you have 3 components and you want to compute their cross product, and one of the ways that you're taught is that you should put them into a determinant with basis vectors, and then you basically operate out the determinant, right? Does everyone remember this definition, this formula, right? It's a nice way to compute cross products. So when you realize is that, okay, let's look at that formula, right? Maybe I should have copied it here, but you all see the 3 vectors, I, J, K, for example, or A1, A2, A3, and you have your 2 vectors in components, right? Like the first 3 components and the second 3 components. Then you realize, so this formula, the determinants have to be square. So it makes sense. We are in 3 dimensions. So we have 3 basis vectors and then 2 rows of components that are 3. Okay, that makes sense. But then you realize, wait, so what if I changed my dimension? Let's go 1 dimension lower, see what happens, right? So if we go 1 dimension lower, suddenly you have to make a determinant of only a square of 4 elements. And one of them has to be a row of basis vectors. So you're kind of forced to be in 2 dimensions, right? So, okay, in 2 dimensions, I have 2 basis vectors. And then the second row has to be the components of a vector. Now, we are.
Carlos, for these kind of things, if you want, you can just use the whiteboard. That may make it
maybe
easier.
Maybe that's easier. So
if you just write it down, it'll be better,
Yeah. So problem is my tablet is not connecting to Zoom recently. And so I'm thinking if I want to show, let me just...
Otherwise, you can just type it over here on another Mathematica notebook.
Yeah, but let me just get the... Yeah, what is the quickest way? Sorry, I was not intending to, because I saw some people nodding at the algebraic part, so I want to give it some detail. So I think I do have this formula somewhere that I can just copy and paste the image very quickly. Just give me a moment.
Sure.
So
just open the documentation for the cross product.
Oh, really?
Already notebook. It's probably there.
Okay, so
Maybe not.
I mean, I will just write it. If I just do, I mean, I can just type it out, right? Like if I just do determinant with, no, it's not there. I mean, I can simply just type this out, right? So the case that everyone knows should have this kind of shape, right? Where you do say x, x1, y1, z1, and then have x2, y2, z2. Right. And so if we do the error.
It's a slash, not backslash.
Oh. Yeah. So this is the case for the usual cross product. Now, if I just simply take this and reduce the dimension to 2, then the basis vectors have to be 2, and then I only have one row left, so I can really only leave it like this, right? So that's the shape of that determinant, right? So if you think about this, right, you can, so I guess I can compute the determinant of this. That should be symbolic, right? So you
By the
get,
way, you can also do cross of a single vector, because the cross also generalizes like that.
oh, really?
Yeah, cross of a single two-dimensional vector. Just x1, y. Oh, it assumes the basis, of course. So yeah.
Yeah, of course. So that's exactly the output, right? So this is basis element 1 with component 2, basis element 2 with component 1 but negative, right? So as Nick just pointed out, you can just do the cross of the vector. That's what this means, which is the same as doing cross here, right? Of these two, right? Which will give you the formula that you are familiar with.
No, don't put it in there.
Oh, no. So with actual argument, yeah. So this is the usual formula that you're familiar with. And it's convenient that Mathematica actually knows about this, because this is the point I'm trying to make, that when you go one dimension lower, cross still defined. This is the cross of a single product. And what it does, if you notice what this is a rotation of 90 degrees, right, in the plane. This is basically applying the counterclockwise 90-degree rotation, otherwise known as the complex structure of the plane, right? So it turns out that the cross product in 2D is the complex structure of the two real dimensional plane. That's something you learned today, maybe for the first time. I learned this about 3 years ago, and I don't have anything to do with it, but it's good mathematical folklore to know. Now, okay, that's going down. Obviously, we go down to dimension 1, nothing happens because we don't have an operation. There's not enough space in the formula to feed any arguments. But we can go 1 dimension higher, right? In fact, we can go as many dimensions higher as you want. Like if I just take this and I increase the dimension by 1, so I should add 1 basis element over here, and therefore I should add another vector as well. But now the vectors, of course, have 1 more component because they are in 4D, right? So I have to add some t, for example. So I just add t3 over here, and I add t2 over here, and I add t1 over here. And so you get a determinant of this shape, and you compute it out, and you get a big formula. But at the end of the day, what you have is the 3 vectors operating into another vector, right? So you have an algebra structure again, right? So notice the pattern here that when we are in dimension 2 and we have 1 argument, we have a unary operation, because given 1 vector, we get another vector. That vector is just multiplied by I, so to speak, right? It's just multiply, so rotate 90 degrees counterclockwise in the plane. In dimension 3, we have a binary operation where you feed 2 vectors, and what you get out is the cross product in 3D. When you are in 4D, you have an operation that you feed 3 vectors into it, and then you get 1 vector out. The general construction, the general concept that is behind all these constructions, the commonality to all the arities and all the dimensions, is what I call here the oriented orthogonal complement, right? And what is this oriented orthogonal complement? Well, if you're in n dimensions and you have some notion of dot product, so some notion of scalar multiplication of vectors, right? You realize that it is well defined to say whether 2 things are perpendicular or orthogonal, right? And if you give me a collection of n-1 vectors in n dimensions, you know that at most n-1 vectors will span a hyperplane in that space, meaning a codimension 1 subspace of that space, right? And so because that's the case, you know that by the property of orthogonality, that you will have 1 orthogonal dimension to that hyperplane, right? Or you will have lower dimensional span of the vectors, in which case you will have more higher dimensional complements. So the product is defined in the following way. When there is indeed a hyperplane defined by all the elements, meaning they are all linearly independent, right? You're going to have a non-zero output. Otherwise, you're going to have 0. Right? So the first thing that the cross product does is it measures whether your collection of vectors is linearly independent, which is quite useful. If it's linearly dependent, you get 0. If it's linearly independent, so it expands the maximum dimension for that number of vectors, then you're going to get some non-zero vector. And what that non-zero vector is precisely is the single vector that makes the entire set of vectors ordered in a specific way. This is a list of vectors. This is not just a set. This is actually a list of vectors because it gets input into an operation as a tuple, right? Is the unique vector that makes the tuple of all n vectors, the n-1 arguments plus the output, into what we call an oriented orthogonal basis, right? And so so that defines the direction of the vector. The norm of the vector is defined by that when you compute the volume of the element of space with the n vectors, you get exactly the volume, the area or volume of the hyperplane vectors, right? So this is the intuition that in 3D, the norm of the cross product is the area spanned by the parallelogram of the 2 vectors, right? So when you go to higher dimensions, the norm of your n-ary dot product is going to be the basically the volume of the n-1 volume of your vectors, right? So this is all fairly standard vector geometry stuff that many of you I'm sure know, and it's not really sophisticated. But the thing that gets never mentioned when people study these things is that, well, actually, the cross product is the first example of a Lie algebra. And it's funny because when you study these things, you never are concerned with the Jacobi identity of this product, because you have to write two cross products, and that's kind of the difficult double product, right? Like the scalar and vectors is fine, scalar and just factors is okay, but that double cross product is difficult, and it's just difficult because it's non-associative and it involves this Jacobi identity. So it so happens that when you go to higher dimensions, so in particular in dimension 4, this ternary product, imagine that you denote it with this bracket, satisfies exactly that equation, right? So if you are concerned that despite of how simple and elegant and natural the definition of a three Lie algebra bracket is, if you're concerned that there might not be natural examples, just think that you actually already knew examples because you knew how to do cross products, so you have examples of this. So anyway, so this is just to say that there's an extremely straightforward story to go from binary binary Lie algebras to n-ary Lie algebras, very well motivated by examples, with very clear applications in geometry, because these products are computing orthogonal complements of codimension 1, which is something even in general relativity, that's exactly what you want to think about in, for example, your light cones, right? You want to have the 3+1 decomposition or n+1 decomposition, and so if you take n space-like vectors into this kind of cross product, you're going to have a time-like vector as an output, and so on. So the point is, when you learn a little bit more maths on the Lie algebra side, and you learn that physics is all based in gauge theories, and there's all this field theory kind of industry going on, you realize that what you normally care about for the full theory is the group that integrates the Lie algebra. So it's not the infinitesimal transformation, but it's the full transformations that, for a lot of applications and computations, you can restrict infinitesimally, but as a whole is a group. And then when you're doing your group theory classes and learning your basic Lie theory, you come across the result that this very important Lie factor, as it's called, that tells you that Lie algebras are in one-to-one correspondence with simply connected Lie groups, right? That is to say, if you give me a Lie algebra, I can integrate it, basically exponentiate the Lie algebra into a simply connected Lie group. And if you give me a Lie group, I can compute the infinitesimal Lie algebra of the Lie group, and these are in complete correspondence, right? So if you begin with a simply connected Lie group, you will get a Lie algebra that is exactly the one that exponentiates back to where you start, right? So this is an extremely important example, extremely important result. And then the question naturally arises, okay, what if I define these three Lie algebras, right? What is the exponential of a three Lie algebra? What kind of object is there? And your human brain tells you, well, it should be some kind of ternary group, right? That just has a ternary operation that is kind of associative, like groups are associative, and so on. So it turns out that this completely fails. There is not only we don't know what kind of algebras should be candidates for exponentials of three Lie algebras, but we don't even have candidates. It's not like we have like 5 or 10 or 100 candidates, and we're trying to figure out which of them is an exponential of a three Lie algebra. Is that we don't even have candidates for what could be. I mean, I guess there are two very easy candidates, but are trivially disproven to be exponentials of three Lie algebras. So okay, we have a couple candidates, but they are kind of the obvious ones, and they don't work at all. So this is all propaganda for the ternary bug, basically. I mean, this is, as I said, my talk is not, despite this being almost 30 minutes into my presentation, the presentation is not about the algebras, but I really want to give you a very concrete flavor of why you should care about higher order mathematics, and particularly these higher-arity algebras, because in a way, these structure, I mean, the cross product is studied in high school, right? This is not, you know, the super advanced fancy mathematics that people are studying today in math departments across the world. This is fairly pedestrian mathematics, right? It's just cross product, and generalizing them to arbitrary dimension, you find these algebras that have this completely natural question that is not only unknown because of technical complexity or because it is very hard, but there's not even a candidate for what an answer would be. So that proves to you that there's a hole in mathematical knowledge. There's a proper hole that we just don't know how things look like in that direction if you want to go and do those kinds of mathematics. Okay, so this was a very long-winded introduction to why one should care at all about higher-arity operations. A very specific example, but I think a very basic and natural one that everyone understands. So another way to kind of jump into the higher-arity territory is to consider matrix multiplication, right? So matrix multiplication, I want you to think, if you've learned fancier multilinear algebra and you know about tensors and with covariant and contravariant indices, and you know about dual vector spaces and all these kinds of constructions, and you understand them as monoidal categories. Forget all that, right? If you don't know about it, no problem. If you know about that, forget it. So we don't need all that technology. And I really want to, again, pull you back to high school when you're first learning about matrices and vectors. And probably when you were that age and you were told about vectors and matrices, those things meant arrays of numbers. They didn't mean geometric objects that have transformation properties. They meant, you have a collection of numbers and you write them down and you start to do operations, column by row, and you start to do your little calculations. So that's exactly the level of mathematics I'm asking you to to kind of load up in your memory, not further, right? And it sounds like a joke, but it is important technically to stay there. So in that realm, a matrix, I mean, I'm going to use this word array, right? Because it's more neutral. So it's like a matrix or a vector, but without the loaded meanings of linear algebra, right? So an array can be a single number if it's just a scalar, can be a one array if it's a vector, like a list of values. It can be a table of values like a matrix, but then it can also be higher dimensional arrays, and what people would call tensors. And again, I'm gonna not force this multilinear notation or terminology on this. So with that understanding, matrix multiplication happens to be this particular combination of index summations and multiplications, right? So you give me two arrays, A and B. It's indexed by their indices. And then you take elements from the first, you multiply them with the elements from the second in this particular pattern, right? So this is what we call a contraction along the first and second index of the arrays, right? Because we're just summing over the index P, which is second for the first argument and first for the second argument. So if you do this, there is nothing stopping you from generalizing and saying, well, if I have arrays that have more indices, with two indices, we could also generalize. There are a couple more options that you can do that, not only this one. But then you would think, what if I just contract things in such a way that I am left with the same kind of object? So what's special about this product? If you think, what are all the possible ways in which I can define something, some kind of product that looks like this? There are not that many, right? It's just a combinatorics of how you deal with indices. And if what you want is that for arbitrary sizes of your arrays, you want two arrays operated together and you get out, again, a two array, it turns out that this operation is unique, right? Of all the possible combinations you can do, again, there's not that many, but of the ones that you can do, this is the only one that is completely flexible, that doesn't require you, for example, that all the indices are the same, because in that case, you could do something like the Hadamard product, which is just multiply everything together, right? Or sum everything together. We usually don't call that a product of matrices, but it's just an operation defined on matrices. So it turns out that if you're dealing with rectangular matrices, right? So arrays that have two sizes for dimensions, and you want to constrain an operation that stays within that category of objects. So it inputs two objects with, or two arrays with 2 dimensions, and outputs an array with 2 dimensions, or 2 indices. This operation is unique. There are no more options, right? And in fact, it's unique, and you need to assume a constraint, which is called a conformality condition between the 2 arguments. It doesn't work for any pair of arguments. You have to have 2 arrays that share at least 1 index of the same size, right? So otherwise, they can't be stitched together and form a new matrix. Again, it is very important that you unload what you know about linear algebra, that matrices are basis independent, are basis expressions of linear maps that are independent of basis. All that stuff I really want you to forget about. We can bring it up later, but this is really just at the level of data structures, just as arrays. That's the kind of the mathematical mentality of, I want an operation between similar objects to output similar objects. That's what you call algebra typically. In that sense, this operation is unique. Now, if you generalize and you say, well, now my objects are going to have 3 indices instead of 2.
Carlos, can I ask you a question?
Absolutely.
So you say, I don't understand what you mean by unique exactly. Like,
Yeah.
What if I just define something like the same thing you have there, but I just take the squares instead of A and B?
Okay. Yeah.
Just as an example.
Yeah. I should have qualified a bit the statement. So the statement is to say that you're only allowed to bring these linear combinations of your elements, right? So you want to state polynomial on the number, on the arity, basically.
I see.
Yeah. So
Okay.
I should have constrained a little bit my statement. So it's not, obviously you can define a wide range of operations with this thing, like massive range, infinite, right? Like it's not at all constrained. But if what you want to do is to generalize matrix multiplication, so you want to constrain that you always have 2 factors, right? And you're doing some kind of generalized arithmetic with your scalars of your matrices, then you would never use like powers of the entries. You would never use any functions. You would never use factors that are strenuous, right? Like, times 2 is different. Yes, it's technically different, but you pull the 2 out of your sleeve. That wasn't canonically given by the matrices, right?
Okay, and then I see. Thank you. And then the Hadamard product is bad because it doesn't. You don't know how to do it for like rectangular matrices, or
exactly. Yeah. So
Okay.
Hadamard product is restrictive in that you first want to ask, I have the whole family of matrices, right, of all possible sizes. Do I have a well-defined operation with these constraints that that it stays polynomial in the entries? The answer is no, because it doesn't work for arbitrary sizes of matrices. But when you see that you can constrain one of the sizes, one of the index sizes of the matrix, and then you actually have one, right?
Okay.
And then if you restrict to the 2 sizes of the matrix, then you have more, because you have Hadamard and addition. And then when they are squared, there's even more, and so there's a
I see.
But when you take matrix multiplication as a template, it turns out that there's only that one. And in fact, if you're mathematically minded and more algebraically minded, it's the first operation that you can define with just numerical arithmetic. So imagine that your matrices are valued over the natural numbers. That is associative but non-commutative, and this is kind of the call of fame for matrices historically, right? That's why this is we're looking for something. Dirac was kind of like, I need something in my equation that is associative like a number but doesn't commute, because I need the permutations to matter. So yes, in that sense, it's unique, right? So in a sense, this gives you the warmth feeling of binary land, right? The warmth feeling that all you know about matrix multiplication is basically the end of the story, right? And that's all of it. However, if we go to ternary world, right, and we upgrade, go to the next valley, and all the inhabitants here are 3 index guys, then there are more possibilities. Like obviously the combinatorics blow up, like there are many more, not infinite, but many more. But the question could remain the same. You could ask, okay, what are the products that are polynomial in the number of arguments, right? So, but keep this constraint of if I have 3 index objects in, I want 3 index objects out, right? And I want also, I'm going to introduce another notion, which is I want some notion of symmetry between the indices, right? That I want to keep things a little bit balanced. Just like in matrix multiplication, you have a notion that you're contracting first and second, or second and first, right? And so you want to somehow have a sense of symmetry, like the way that your arguments come into the equation is symmetrical. So for example, we could have defined a product that basically takes a trace of one of the matrices and then takes the kind of the diagonal of another matrix and then multiply those together. That's a well-defined operation and it's polynomial and satisfies all the things. But the problem with that operation is that it is asymmetrical. So A and B are entering into a completely different role in the operation. So for that reason, we constrain for symmetry. Now, these are a couple of examples that can be defined, right? So in this case, A, B, and C are IJK index arrays, and so this particular formula over here, the first one, tries to mimic as closely as possible the formula of matrix multiplication. So if you've been kind of inspecting the formula, you realize that IJK are free indices, right? They are not summed over. You're only summing over P, just like in your matrix multiplication here. And P is following a very similar pattern to what happens in matrix multiplication. P is a shared index between the last index of the first argument, the second to last in the second argument, and so on to the first argument in the last argument, the first index in the last argument. So basically, P kind of walks through the possible locations in the index site, and then as you cycle over the arguments. So that operation is called it has a name. People have actually studied it. From 1990, there was a couple of papers written about it, and ever since we've contributed a few more. I myself have written a couple of papers about this product. This is called the Zapata-Carratalá product due to that original paper. And we don't know much about this operation. Something that is very shocking, perhaps, is that this is non-associative. So in the same way that the matrix multiplication here works in a way that A, B, and then C is the same that first A, then B, C, right? This is not the case with this Zapata-Carratalá product. And not only that, but actually work that I did with Xerxes here that you all know showed that this product has no known axioms at all up to size 7. So 7 is the number of arguments that you would enter, right? Like, so associativity that you would write something like this, right? You have A times B times C, and then you want to compare this to, A times B times C, right? In this kind of, in this kind of formula, right? This is a 3-element axiom, right? Because you're involving 3 generic elements at most. Now, of course, the ternary version of associativity would look something like, I will drop the symbols, and basically you will have A, B, C, D, E, and then maybe you want to relate this to something that might look like this, right? B, C, D, E, and maybe something that looks like this. Yeah, A, B, C, D, E, right? So that is what we could call ternary associativity, right? I mean, if you take 2 associative operations and you put them together, like, one after the other for 3 elements, that's exactly the axiom they satisfy, right? So if you think that what you're operating is binary associative operations, all those terms become A, B, C, D, E, just pairwise multiplications, and associative, therefore it holds. So it's a very reasonable axiom to expect for. And this is a 5, so this is a 3-element. This is a, whoops, that's not. Sorry, this is a 3-element axiom, and this one here is a 5-element axiom, right? So the result that Cecil and I showed computationally, but with symbolic check, was that up to 7 elements, so including a lot of possible formulas, right? And 7 elements means that you put brackets in all possible ways and mix them in all possible ways. There are no known axioms for that product. And actually, a colleague of mine at the University of Colorado Boulder recently told me that thinks he has a proof to show that indeed there are no possible axioms for this product at all. And again, axioms here mean equational identities, right? That should be precise with what I mean there, which are properties of this kind, where you input generic arguments into some bracketings, and that equals some other bracketing of the same elements rearranged in some way, which is exactly what associativity is, and most of algebra is built out of those kinds of arguments, right? Like out of those kinds of axioms. Yeah, Matt, go ahead.
So quick question was the claim is that there are no axioms up to, or is it including 7 elements, meaning we would need to go to an 8th element?
So you would always go for odd number of elements because you have to put brackets of 3. Okay. But the result that we definitely got computationally was that up to 7. So you have 3-element axioms, which is just symmetry properties, none of those. 5-element axioms like this one, none of those. Then 7-element axioms that are like these but with more, right? Like it would look something like this. You write something, inside of here, you write X, Y, Z. That's a 7-element term, and this will equate something here, like over here. I just deleted C, so maybe I put it here, right? X, Y, Z, right? This would be a 7-element axiom.
Okay. Is there any intuition on why, or if you're getting to that, please continue.
No. So we went up to 7 just for computational limitations, because it was, the higher you go, the more difficult it is to prove. But as I said, my colleague in Colorado actually thinks he's found a generic argument that shows that this particular product has no known axioms, right? Which is at this point to be expected, I think, because if you go up to 7 elements and you try everything and you find nothing, it'll be a bit strange that you have to go up to 9 or 12 or or 11 or whatever. It's weird. So anyway, I'm trying to give you the sense of weirdness of these things, right? Like the moment that this looks quite inoffensive in some sense, right? Like it's like, yeah, these are okay, cubic matrices, not quite the same as you're familiar with, but okay, 3 indices. It's not crazy from 2 to 3, and from 2 arguments to 3 arguments. There's kind of a rhyming of the arities and the number of indices, right? So you might think, okay, then maybe these things follow kind of a natural mathematical language, right? And it turns out that they don't. And this is the big Pandora's box that I opened kind of 2-3 years ago now, where clearly these things are weird, right? Like we just don't have enough mathematical insight. So hopefully by the end of this presentation, I will turn the tides a little bit on the perception that these things are a bit hopeful, because and by the way, sociologically, what we can claim that these things are mathematically hopeless, because mathematically people have just not worked on this, right? Like they just decided that this is not for them. You can count with the fingers of your hands the number of papers written on the Zapata-Carratalá product specifically. And that's like, if you try to compare it to matrix multiplication, I don't know how many papers, but probably millions of papers, right? So that's not a fair comparison, but anyway, the point is that even the most direct, most obvious analog of matrix multiplication, which is the smallest, by the way, because you could have higher orders of more arity, more indices, and they could also be analogs. The smallest, larger analog of matrix multiplication itself is almost completely unexplored. I mean, there are a few papers, and I know the authors that have published them in the last few years. But these guys, we're all kind of in conversation. We're all very clueless about this product. And up until now, we are not even sure if it had some kind of axiom property like associativity. We knew that traditional associativity fails because that's easy to check. It's very easy to check that one action holds or not, but it's very hard to say if there are no axioms at all, right? That's quite difficult. So anyway, so I wanted to give you the sense of weirdness, and what I was going to say is that hopefully by the end of this talk, you would have the sense that this hopelessness of hierarchy can be at least tackled or approached with this hypergraph rewriting technology that we, fancy stuff that Nick and I have been developing, and that, thematically is within Wolfram Physics project and all these things. So let me give you a hint of.
Carlos, before you go to hypergraphs, I have a question.
Yeah, please. Yeah.
Because instead of like considering matrix multiplication and generalization of this, have you considered like another ternary back is that we have like this duality of covariant, contravariant indices, and we use matrices as basically just like some kind of metric that we compute angles between vectors, and the ternary generalization of that would be like what would be the generalization of angle between three vectors, right? And whether it's basically equivalent to just generalizing matrix product.
I love that question, Nick. And I actually I think I have a notebook that is ready to show something. I think this one as well. Let's see. So I love that question. And I make it a bit bigger so you see the definition. So I pick up your line of thinking, I think, and you tell me if I understood exactly where you were going. So you're saying is think about matrix multiplication more like taking a dot product, right, and see how you generalize that dot product, right?
Yeah, something like that.
Yeah, between vectors, exactly, between vectors. Yeah. So the idea is that, okay, what is a dot product? I mean, here's again, like the exercise, go back to high school, unlearn a bunch of stuff, as you would see, this is kind of a theme for my kind of research, that I like to go back to my childhood, mathematical childhood, and just like revisit. So the binary dot product, everyone knows, you take two arrays and you just, arithmetically compute this kind of average and or, right? So it's basically saying, this component and that component, and then you say or that component and that component, and so on, right? So you could do a unary dot product that's very boring. It's just adding over it's like a trace of the vector. That's uninteresting. But you could certainly go higher and do ternary and quaternary and so on, which is you basically just replace the number of factors per summand, right, in each of the terms. So the reason why I'm mentioning this is that yes, you can do that, and indeed the triple dot product corresponds to exactly the operation that you are doing here. Let me see if I find so the operation that's going on here, just like that matrix multiplication can be understood as you take a row vector and a column vector and you dot them together, right? That's an understanding also probably dating back to high school.
Yeah, it's a matrix in between.
Yes, it's exactly, or it's a like the metric matrix in that sense. For the triple product, I mean, for the Zapata-Carratalá product, you can notice that if you take rows, columns, and depths of your cubical matrices, the operation that you have to do to form this product is exactly the ternary dot product, right? You take a row, a column, and a depth, and you dot them together, and in fact, that is exactly the condition that you need the arrays to satisfy to be able to be multiplied. So the answer to the question is yes. So if you want to go into that direction, something quite interesting happens. Well, I mean, just to because this part of the talk is about the weirdness of hierarchy. I'll show you a couple of visualizations of the ternary dot product in 3 dimensions, so everyone can visualize it. So in this notebook, I compute for 3 given vectors in 3D, 3 products. Basically, 3 products that are defined by being multilinear and up to sign, being being just a well-defined scalar for the whole set of 3 vectors. So what I compute is the first one is the 3 dot products summed together. So it's kind of an average of dot products across the family of vectors. The third is the volume. So that's just the determinant of your matrix made with those vectors. So the volume of the parallelogram. And
Carlos, you may expand the size a bit.
oh, sorry. Actually, are you seeing?
Yeah, we are seeing, but you could make it a bit bigger. It'll be better
Okay,
even
okay,
for the recording as well.
Okay, so you're seeing the tridots and
Yes.
Oh, okay. So yeah. Okay. So I'm computing 3 things just for reference, right? The important one is the middle one, what I call the tridot. The tridot is the ternary dot product, right? And I'm going to show you something extremely counterintuitive. So just be warned. So I'll hopefully we'll make that. So just as a warm up, if I have the basis vectors over here, the volume is 1, obviously, that's the unit cube. But obviously they are all mutually orthogonal. So all their dot products are 0. So the sum of the products is 0. And the tridot, because they have components 0, 1, and 0, 1, 1, 0, and so on, that's also 0. Okay. Now, what if we take like an equilateral triangle embedded in 3 dimensions? So this is a flat set of 3 vectors. Well, you obviously get volume 0 because this is two-dimensional shape. And then bidot and tridot have some non-zero values. Okay, whatever. So clearly the tridot is not measuring some kind of volume because otherwise this will be 0. That's why I wanted to show this one. Okay, what about some random stuff? Just generate some random vectors. So, okay, you get some numbers that they don't seem to be particularly, related in any way. But then here comes the very counterintuitive thing. So imagine that I take this particular set of vectors. So this is basically, as you can see, right? This is the vertical kind of unit vector, and then 45 degrees to the right and 45 degrees to the left in the YZ plane, for example. Right. So this particular combination of vectors has volume 0 because it's in the plane, bidot whatever, square root of 2, some value, and tridot 1/2, whatever, some other value, right? So what happens when I rotate this? So this is just the rotation. This is 45-degree rotation of the same shape. Obviously, I just rotated, so the dot product is not going to change because it's a symmetry of the dot product. So my bidot is still square root of 2, but suddenly the tridot has vanished. Right. So, I mean, this is not surprising when you know that the tridot is actually looking at the components and checking whether some of them are 0. And it so happens that here, first argument and third argument are basis vectors, so they have 2 0 components. So they are going to show up in the triple products, and it's going to kill everything, right? So this is very strange, right? Because this clearly it means that the tridot is not capturing anything geometric in the usual sense of the word, right? And in fact, it's not hard to prove more generally that if you have a value, you have a collection of vectors that give you a value for the tridot, you can find an arbitrary. You can always find a linear transformation that would make that value be another arbitrary value, including 0. So, in other words, the tridot does not know about your linear theory of vector spaces, right? Also, interestingly, when you define the dot product, you can ask about the symmetries. I mean, that's why I was talking about rotations here. And then, the symmetries of the dot product in 3D is the well-known group SO3, blah, 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 all this, or O3 and so on. And it turns out that you can ask the same about the tridot, right? You have a way to compute a number for 3 vectors, and you can ask what transformation do I have to apply to these 3 vectors so that the result of the transformation leaves the tridot unchanged, which is what you ask in the case of the dot product for symmetries, for rotations or reflections. And it turns out, and this is again quite counterintuitive, turns out that there are no valid transformations that preserve the tridot. Again, linear linear mappings of the space itself, right? So
in 3D or in general?
in general.
in general.
In general.
So if you
So
think of it as like a generalization of your reflection and rotations, but you're reflecting in some kind of volume element instead. It's
yeah,
it's not generating a group, something like that.
yeah, maybe something like that. So my intuition about this result is that it's the wrong question to ask whether there's a set of transformations that preserve the tri-dot product, because I mean it's not the wrong question, by the way. This is done all the time in physics, right? Like the tri-dot, I should be very clear. The tri-dot is a trilinear form in your vector space. So it is multilinear in all the arguments, and so in a sense it is a fairly tame familiar object in that realm. But it so happens that when you ask in a conventional, either group theoretic or linear algebraic way, what are your symmetries? Meaning, what are the linear transformations that you can apply to all your arguments so that your value doesn't change? The answer comes out empty. I mean, technically comes out as only the identity, right? Does that.
That's why you're not going to put it like inside of your Lagrangian, because it's not going to be invariant in respect to your usual groups, right?
Exactly, and that's exactly the point. With respect to usual groups, that I think is the key. That's my intuition. My intuition is that what is lacking, because obviously this thing is very concrete. It's like you're multiplying numbers together, so there should be some kind of symmetry to this. I mean, it's very unexpected that there will be no symmetry whatsoever to this. But my intuition is that the notion of symmetry that applies to this object, or an answer in your question, Nick, to the notion of ternary angle, or this idea of you have covariant and contravariant as the two sides of the coin. Now you have three things, right? You have, I like to call them red, blue, and green kind of vectors, right? Because they are in some kind of triality, right, of relation. It turns out that I think we are lacking the right notion of symmetry. We're probably some kind of ternary group of symmetry applies, but
Well,
because we don't have the language.
we have triality in physics already in the flavors and colors. You just
Yes.
have to have a higher dimension when the triality appears, like something
Yes.
like
So
dimension.
I will comment on that. So the triality found in like flavors and in physics, the people that have identified in physics, is not this notion of triality. In fact, we are in communication with some of these people that like John Baez and these people have wrote about trialities, because I mean it's a bit of a minor dispute, but we want to have them acknowledge that the proper notion of triality is this. We just don't have a good theory for it. But their notion of triality, actually, when you break it down, their definition of triality is a trilinear form such that whenever you curry a non-zero argument in the three, you get a well-defined non-degenerate bilinear form, right? This is not the case for this, right? For this, I mean,
I think their notion of duality is basically the duality is just like its cycle in free. It's like multiplying by third root of unity or something. That's why you're cycling between three flavors at the end.
okay, okay, so then that's more like a set three grading than a triality, but yeah. But these things are definitely connected. All I'm saying is super weird stuff, right? So the question of, you could try to generalize in that direction of thinking of dot products and like covariant and contravariant. You have to, in fact, when I say in my notebook here, I say arrays, not necessarily tensors. That's where I'm pointing at, right? Like this indices ijk, it's not one contravariant, the second covariant, and the third contravariant again. I mean, it's ijk, and if you want to really take it seriously, it would be I of type red, J of type green, and K of type blue, or something like that, right? So it is, again, another open-ended sort of unknown territory to go down to. Sorry, Matt, you had a question.
Okay, here's a completely naive question. You say that there's no reflection there. I believe you. So like if we were to do like a rotation, like multiply it by 2 pi or something like that, there seems to be no.
Yeah.
I'm gonna stop talking.
Yeah, no. So sorry, Nick. I don't know if you had some reply because
I was going to ask another like question about because you mentioned covariant, contrariant. I remembered immediately what is the actual source of that? Is the change of coordinates, and we usually use like a Jacobian matrix for that, right? to change the coordinates. So it's basically generalizing it to reality. You need to generalize what the notion of coordinate transformation is between this,
yeah.
whatever it is.
Oh, no, exactly. And just quickly to Matt's point, yes, what we checked is that there's no possible linear transformation, not even rotations or reflections, but there's no possible linear transformation, including scalings and other things, that preserves the product generically, right? I mean, there will be some products that are preserved, obviously, but generically, for all our arguments, it doesn't happen. So yes, Nick, that is exactly my intuition. The intuition is that the change of basis needs to be reconsidered, right? Like what a change of basis is a binary notion because you're going from one base to another.
Well, maybe the basis itself. It's like now we have not the vector basis, but like a bivector basis or something. I don't know.
maybe something like that, or simply, I think it could be as simple as if you had three bases, right? I mean, like crazy idea, right? I mean, you're talking about changes in bases all the time, but if you had three bases, there is a meaningful notion of a linear relation, right? And these are more technically thought of as subspaces of the direct products of your vector spaces, right? So you could think, are these three bases in linear relation? It doesn't mean that there's a map between two of them, right? I mean, a collection of three maps between the three is an example of such a thing, of a relation of linear bases. But more generally, you can just think of a subspace of, your space cubed, right? And as a vector space. And in that subspace, you could say whether things are, if they belong to the subspace or not, you can think that they are related. It's a bit like thinking, to ask whether there is an isomorphism between the two bases, which is the question whether what you did is a base transformation. You can ask element-wise whether this maps into this element, right? Is E1 equal to phi, whatever, epsilon 1 or something, like that equation. You can rephrase by saying, is the pair E1 and epsilon 1 in the graph of the map, right? And the graph of the map lives as a subspace in the Cartesian product of the spaces, right?
Yeah, maybe they just have to consider multiple spaces. It's like the
Yeah.
basis transformation happens in the same space, like the tangent space. But what if there are two tangents and we have two frames in both of them, and maybe they're actually connected with each other with this triality or whatever.
Yes, something like that. I mean, my intuition, again, is exactly in that direction, that you have to up the arities everywhere in some sense, right? Like you can't just. The problem, I mean, the problem that seems to be that if you attack these objects with conventional mathematics or conventional thinking methods, it's failing, right? That's kind of the takeaway. So anyway, maybe let's leave it for the end if there's more questions on this, because again, this was mostly to give you a sense of weirdness. I think that we have accomplished. I think there was enough weirdness accomplished. So let's look into hypergraph briefly. So hopefully you've seen hypergraphs before. These are discrete combinatorial objects, right? I'm gonna consider directed hypergraphs, meaning that my edges are tuples, right? They have a first and a last, and they are ordered elements within them. And the obvious connection between all that I've been talking about, these higher-arity operations of matrices or arrays, and what will come next about hypergraph rewriting is because if you want to express the adjacency information of a hypergraph, and by the way, adjacency information of a hypergraph is basically the hypergraph, right? That's essentially what it is, because we are not assuming any labels or any weights or anything like that. You can capture those things by labeling or ordering your nodes, right? So you do 1, 2, 3, 4, 5, right? They have some sequential labels. And then what you do is you translate the adjacency data, meaning the edges, into array objects, right? And so here actually the order of the elements is a bit jumbled up, but basically this is like the adjacency matrix of a hypergraph. If you've seen the adjacency matrix of a graph before, this is like the adjacency multi-array of a hypergraph. So how do you parse this? Well, look that there's two unary edges, right? And the edge list is like the node 1 and the node 5 alone as sort of self relations. That is captured here. You say there is a self relation in 1, there's a self relation in 5. Again, this a bit jumbled the order, and then no self relation, no self relation, no self relation in the others, right? That's how you read that first column. Now, for the binary edges, like this 1, 2, 4, 3, 2, etc., you get just like an adjacency matrix. So you get a matrix, this matrix, right? And you have just zeros and ones depending on whether you have a edge for that. And just to be fancy and to visualize, Nick made this very beautiful thing where you can see your array in 3D, and you can see that there's like in position 2, 3, 1, there's a 1 in position 5, 4, 2. So we can check, right? 5, 4, 2. What? Huh. Oh no, this is jumbled. Sorry, the order doesn't match the actual levels. But anyway, so you can see that there's at least reality check. There are 3 ternary
It was
edges.
5, 4, 3, I think.
Yeah.
Not 5, 4, 2, right?
5. Yeah.
Am I tripping?
No.
Oh
but
no, it is
these
5, 4,
orders,
2.
these orders changed, as I said. It
Okay.
jumbles the order when I render this.
And that's shown as the like shading, right, on the hypergraph.
Exactly. The shading is these 3.
Yeah.
The actual data,
Oh,
right?
yes.
And
Okay.
graphically, it's the shading.
Okay.
And then in the matrix, you have, the actual indices are not going to match, but you have a 1 over here, a 1 over there, and a 1 over there, and everything else is 0, right?
Okay, cool.
So anyway, so this is how you make contact between these two things. You realize that actually hypergraphs and higher order arrays are sort of interchangeable, right? Like we have this way of going back and forth, at least between well-defined categories. And so what I'm going to introduce is the concept of hypergraph rewriting. You've probably seen it before, but I'm going to introduce it in a very specific way that will be useful for our purposes. And we will do it with our own Packlet, which, as I said, you can download this and you can play around with it. So first, we are going to define a rewrite rule that is extremely familiar to everyone, I hope, which is effectively a transitive closure, right? Or completion of paths or something like that, right? Or if you're more mathematically minded, this is effectively composition of morphisms in a category, right? So what you do is you take such a small graph with 2 edges, 1, 2, 2, 3, and you say, well, because 1 was connected to 2 and 2 was connected to 3, I'm going to connect 1 and 3. So it's like, doing the shortcut. It's closing the path. So what happens is once we begin with a state like this, a big hypergraph potentially, in this case it's just a graph, just for concreteness, and we apply this rule over here to this state. In the first generation, so this is the first here, 1, we get all the possible outputs that you see the pattern being matched to the unspecific locations here. So here, 1, 2, and 3 are actually patterns. I could change the names here and actually give it generic names like X, Y, Z or something, because these are going to be patterns that are matched. And so the output of this, the first generation of this, is you go hunting for the pattern. So the first one here is the 3, 4, 1 pattern, right, which coincides, and it gets rewritten to a single edge between 3 and 1, right? You can see it very clearly. We went from having edge 3, 4, 4, 1 to just deleting those, because that's what the rule tells you, that if there were 2, now there's only 1, and we draw a single 1 from 3 to 1, right? And that was one case, but again, in the first generation, we checked for all possible matchings. And so, for example, here we found the pattern 5, 1, 2, right? And we had edge 5, 1 and edge 1, 2, and that becomes an edge 5, 2, right? So anyway, that's That's the logic of hypergraph rewriting, right? Like in this case, graph rewriting. Similarly, we find the cycle here in the middle. We have three possible rewrites of that, and it's exactly the same logic. We can apply it to other hypergraphs that have this. For example, these three triangles, these are oriented, remember, because that's where you see some arrows. It forms kind of a bigger triangle. Now, this vertex here is not part of the edge, right? This is just floating there. It was like a vertex of three edges, and now it just becomes a floating vertex. So if we begin with this seemingly complicated thing, right, which in disguise is just two of those patterns on the left, we can actually visualize the causality of the rewrites, because the understanding is that you begin with a state, and then you perform the possible rewrites, and then you get new states, and those are, again, as I said, states that can be subject to more rewrites and so on. So in this particular case, there's a very simple story, because you go, there's two patterns. I can match one on the left, one on the right, and then in the end I get this that just has two edges, and because this has no more of these patterns, there's nothing else to do, right? So we can actually drill down a little bit with the hypergraph packlet and the multi-way system, multi-computation packlet. We can see the specifics of how the rewrites happen, right? So in here, you see the initial state, and here you see the rewriting event that took place, right? You see where in red, where the matching happened and what it turned into, and here in red where the matching happened, and you see the states of the hypergraph are shown in the blue boxes, and in the yellow boxes you have basically the events that happened, right? Like what event happened, and then we can draw causal relations between events being connected, meaning that this came after this one because they share the parent, and in the end it's just this with more detail, right? But importantly, we can see if what the relations were between the different rewrite processes, right? Because, and in this case, we have this sort of two parallel rewrite processes, and that's why we can see the causal graph basically of this as these two events.
Can you resize that big multi-way system, because I think it's confusing and the arrows are flipped.
This one?
Yeah, I think it's just a bug, rendering bug.
But this could be.
Yeah, just.
Or else I have to run it, and I didn't want to.
I think it's all right. If you make it very large, then the arrows are in the correct position.
But then I zoom out and make it large, you mean?
Yeah.
Yeah. Right. Yes.
It's confusing.
Yeah. Yes. So yeah, as you can see, this is basically the expanded out version of that rewrite system. Very simple. So anyway, where are we going with this? Let's connect it back to algebra, right? We saw some basics of hypergraph rewriting, and now we want to connect it back to algebra. So let me get back to so let's explore associativity, which is hopefully will be super familiar to everyone. I mean, we are born into associative mathematics since we're 4 years old or whatever. And so let's drill down. Okay, let's begin with adding labels to our objects, to vertices and edges, just in order to keep track of where things are going. Again, from a computer science point of view, that is always there because you need to know where your objects are. From a mathematical point of view, this is important because otherwise you won't be able to see the axioms themselves. So, and now this is not just analogous to category theory. This is exactly what category theory does, right? This is a labeled graph, which is what where categories are built on, right? You have sort of locations, also called objects, that have a name that identify them as objects, and then you have arrows between the objects that get identified with some symbol that tells you that they are the element of a morphism set between the objects, right? So in this case, we have objects P, Q, and R, which are just labeled vertices in the hypergraph language, and morphisms Y and X, X and Y, that are just labeled binary edges, right? And so our rewrite rule does exactly what the rewrite rule we had above did, which was just compose the two and complete the path. But in order to keep track of the names, we are going to label the new one as, you know, the names of the previous two in a sequence, right? In a little bracket, just like you do in category theory. But very important, we are not loading up any knowledge from category theory or anything like that. We're only saying this is how we will label our things symbolically, right? But otherwise, this is just a system of graph rewriting, completely abstract, completely sort of computational in a sense. There's no mathematics yet. So what we do is we define a couple of initial states. First, this generic FG, sort of two-edge state, and then this other longer one with FGH, right? And what we're going to do is, I mean, obviously, if we apply the rule to this one, we just get FG, right? That's uninteresting. Just one event graph, no more sophistication. But when you apply it to this three-edge state, we actually get forking in the stories, right? So we have first FG or first GH, and then both rewrite to a single edge between 1 and 4, but one is labeled as FGH, right? Because we took first FG and then H, and the other is labeled F then GH because that's the order in which we did things. So that's why it was important to label things and name things, because our computational system knows about these differences, but our symbolic or human interface might forget, and that's why we kept it. So you say, okay, right? That seems kind of interesting because we started from a single diagram, and we got two very similarly looking diagrams, and by similarly looking I mean identical up to the label, right? They are both diagrams. I mean, notice that we have, you know, vertices 1, 2, 3, 4, and some edges in between, and we ended up with a diagram that is just one edge between 1 and 4 in both cases, right? So how can we make this precise? Well, let's remove all the labels for a second. So just get back to the original rewrite rule without labels, then apply it to the initial state without labels. And then you notice that this is what we call a confluent system, right? Where you begin with something and something happens, and then you come back to a single state. So it terminates and it's unique. So that's what we call confluent. So let's see actually what happens, right? So what happens is, and again, we have the same issue here. So I'm gonna make it bigger. Yeah, there you go. So what happens here is you begin with the three-edge state, you rewrite on the first two or the second two, and what you get is a single state in the end. And what's important here is that there is overlap between these two rewrites, right? So the edge that gets labeled by G, which is the middle edge of this initial state, make it bigger again, this G edge in the middle is actually seen by both rule applications, right? The first rule application pairs it with F, and the second rule application pairs it with H. And the logic of hypergraph rewriting is that you should apply the rewrites kind of across your whole state and then see the causality of how things evolve, right? So from that point of view, we have some overlap, and that's why we kind of represent that these two events are overlapping, right? In that sense. So let's see an example of that not happening, because it will be important for a point I want to make in the end. So imagine this longer state, right? So now we have A, G, H, I, and I is, so these are sort of 4 arrows that are flowing into this top vertex over here. If we apply the compositions, we clearly are going to get something like this, right? We're going to compose first this side or first that side, but then we'll have to compose the other side. So we can go into the possible ways, but we get to the two arrows in the end. And the idea, so again, there was overlap there because of the vertex, but so in this one, the one I wanted to show, we have FG going into this vertex here, and then IJ going in this vertex here, but this arrow in the middle is not going to compose with either this one or that one, right? So what's going to happen here is, again, you compose one first, for example, on the top here, and then on the bottom, and then you compose the remaining one, so you get a single state in the end. But the difference is now that the events are disjoint, right? As you can see, they happen, in the hypergraph, in the graph, they happen at a separate location. There are no overlaps between them. So all I'm just showing you is that we have ways to measure this, right? Like the causal structure of the system can be traced, and we can distinguish this situation from the situation above. So the takeaway from this section is that let me summarize. What was this? This was a way to discover or rediscover, I guess, the associativity axiom as a property of a rewrite system with hypergraphs, right? And that's something that, if you've studied category theory before, it should be absolutely obvious why this is the case. But if you haven't, or if you have and you want to, take home my message here, this to me is a pretty revealing discovery. It's not, revolutionary for any particular reason just yet, but it is quite revealing in the sense that before, if you wanted to talk about axioms of algebraic theories, you had to either take examples of these algebras and then ask them, are you satisfying this axiom? Meaning, you'll try things and you try to prove whether those axioms are true or not. Or you would have to develop a theory about the axioms, like, universal algebra or type theory and logic and all these things, where you define all possible axioms, and then you go about sort of listing where are possible and their dependencies. But what this allows you to do is to take a system that knows no mathematics whatsoever, is just a computational system, right? That just has some discrete rules that deterministically apply, and which, as you've probably seen already in the context of Wolfram physics and generally about discrete evolutionary systems and computational science in general, this is a very normal thing. Like all automata fall under this category. All these autonomous systems fall under this category. Genetic algorithms fall under this category. So it's very, very general thing. What you have found here is a way to rediscover or identify axioms out of some combination of a rewrite rule and an initial state. So the reason, how did we discover associativity here? We had to be clever to define this particular, random, let's say, rewrite rule. Obviously not random. We are very familiar with the interpretation of this, right? It's like completing a path or composing sort of two transformations or something like that. But from a graph theoretic point of view, okay, this is just one graph into another graph, right, with some labels. And we applied it to some initial state, right? In not all initial states had concluded that this was an axiom, because the ones I tried below, like these ones, this didn't result in any particular axiom, right? But if I was careful enough to choose the rule and then the initial state accordingly, I could actually see, just read off from this diagram over here, I can read off associativity. Just look at the label in the final states, and I say, okay, those things are actually equal because they are confluent and labeled, so the labels are just redundant, right? So I can read off associativity. So you might say, okay, fine, this was associativity, that's something that we all know, no surprises, but can you actually find other algebras or other axioms with this method? And happily, and this was a discovery that I made with Xerxes 3 years ago now, or even more possibly, is that there is a structure called semi-heaps, which you might not have heard of because it's very, very niche and very obscure, but otherwise quite simple. There's nothing complicated about semi-heaps. They are just sets with a ternary operation that satisfies this property. So at the first glance at this property, you would think, oh yeah, this is the associativity that you said earlier. You put, 3 brackets and you move it around. Almost. That's the case for the leftmost and rightmost terms, but the middle term has a little twist, and D and B are swapped, right? So it has a little twist. So whatever, it's a funny looking operation. I have a couple papers on this where we introduce them very simply, and so if you want to learn more, you can find them online. But the idea was that we had not seen this axiom before. We saw it in a paper, Exerces and I, and we were thinking, okay, how can we understand that this axiom, because they were looking for this axiom in the cubic matrix operations, right? In this array operations that I showed above. They were looking for associativity, meaning no swap of B and D here, and for this axiom with the swap. And we thought, what? I mean, associativity I get because it's associativity, but why this axiom? Why are they looking for it? And it turns out that they were looking for it just because some Russian mathematician in the 50s had defined these things, and they have a theory built around them, and so you should care about it. And so basically, because there was an existing publication on this structure, they were looking for it. So we were a bit mystified, and by staring at it, I was thinking, how does one understand this axiom? So the story is simply that the idea that I told you about how you get associativity from diagrams was essentially born at that moment when I was trying to understand this axiom. Because for me, it was very clear. This was the A, B, C, D, E were actually ternary matrices, right? These 3 index arrays that I showed you earlier. And the way I was representing them in my notes, at the time, I was not even thinking about hypergraphs or anything like that. I was representing them with little triangles between the index names, right? Just for simplicity, just because it was shorter. Because I thought, if I have a matrix between I and J, typically you represent like a line, like a morphism between I and J. So now if I have a cubic matrix, I will just represent a little triangle. And so I thought, let me write out what this 5-element expression looks like, and let me see if I can get something out of that. So we did that, and it turns out that you have to write a fish diagram to make it work. So I will omit the story about the matrices themselves. Let me just tell you about the diagrams because it's just simpler and it has the same information effectively. So the fish pattern is a fish made of triangles, right? It's just 3 triangles in this particular pattern, right? X, Y, Z, tail, body, head. Again, this might sound like a joke, but the fact that the anatomy of this hypergraph allows you to distinguish between X, Y, and Z is super important. It will come up in a second, right? Like, that by adjacency properties of this diagram, that X, Y, and Z are distinct, right? There is a edge in the role of a tail, there is an edge in the role of a body, and there's an edge in the role of a head, right? And this is not up to you to decide. And they are well projectable down to a list of, tail, body, head. Anyway, so the way this works is very similar to the previous rule, which is to say, you give me a bunch of vertices, you give me a bunch of edges, and the output is a single edge among the kind of outer vertices of that shape. So it looks very different, of course, than the previous one, but morally speaking, you should be feeling that it's quite similar, right? Because I'm taking a bunch of edges and then looking at kind of the outer vertices, meaning the ones that have the least number of incident edges, and then I'm just kind of collapsing everything to a single edge, which is morally very similar to what you did in the previous case. And so again, I'm going to denote this resulting edge as X, Y, Z in that order, because I can distinguish, tail, body, and head of the fish. So how do you come to the conclusion? Well, you have to choose a clever initial state, and this was the idea that we had, or I had together with Xerxes, that you put the 5 elements that your axiom is going to involve, and you write them out as you would operate them. So you put them in this sort of fish shape, and they just let the rewrites happen, right? So you just apply every time you find a fish, you write a triangle among those vertices. And so this happens, right? You have a long fish over here. And what happens is, I mean, I can make this bigger and explain just over this. How many fishes do you see within this long fish, right? So there's clearly one here on the left, sort of swimming to the left. There's another one sort of following close behind, so it's also swimming to the left. But actually, there is another fish in the middle swimming to the right. Right? There's D, C, B form a fish in the middle. So actually, that's why you get 3 different outputs here in the first generation, because there are 3 fishes in this long fish. And that's kind of the interesting part. So again, I'm just going to label them. Each of them has the 3 arguments they came from, ABC, CDE, and DCB, right? These are, these 3, and these 3 in the middle. And then, very conveniently, these are themselves fishes, right? The outputs are, again, fishes, because of course, the fish on the left forms the head of the resultant fish, the fish in the right forms the tail of the resultant fish, and the fish in the middle forms the body of the resultant fish, right? So very conveniently, they are all fishes. So the rewrite system, again, applies to them. So you have 3 single edge outputs, all with different bracketings, just like before, right? With the same kind of pattern. And so these bracketings just correspond to the order that you did, right? Like, look at the leftmost one. We have ABC because it was on this end, ABC. And so we contract, and then we contract again. So you have ABC, then DE, and so on. And so what's crucial here is that by analogy with, okay, we can unlabel, and we indeed have this, that this is a confluent diagram, right? We also can check this. So this is what we checked earlier, that there are overlaps between the intermediary states, right? So the edges, the edge D and C and B belong to all 3 rewrites, right? When all 3 rewrites happen, the middle edges are seen by that, right? So there's overlap of the events. And so by direct analogy, you should say, right, so I have a single unlabeled output, but I have 3 distinct labeled outputs on the same location, the vertices 1, 9, 2, then this should all be equal. And again, you didn't know anything about semi-heaps before doing this, but by following this recipe of saying, where do I find my unique final terminating output, and how many different ways did I have to arrive there? That is the axiom of that you were looking for. And this is just a direct comparison, right? Like, look, it's A, B, C, D, E. This one is A, B, C, D, E. So those indeed look like the leftmost and rightmost. And then the interesting one, which is the middle one, has A and E in the extremes. That's right. And then in the middle it has the twist, DCB, right? Why the twist? Well, because the middle fish is swimming in the opposite direction, right? So in order to see the middle fish as a fish in the same order as the others, you have to flip tail and head so that it's swimming in that direction. So it's a very visual way to understand that if you know that these kinds of operations can be encoded by the fish rule, you know that there's going to be a flip in the middle, because fishes just behave that way. Like when you do swim in one direction, the other swims in the other, right? So anyway, so this was very important, and this is basically what launched the project. And up until this day, this is what brought me to meet the Wolfram people, and this is how everything started. And this was extremely important because it was a case in which, okay, we technically knew the axiom because we saw it in the paper, but it was a very unknown axiom, right? No one who would have ever cared to justify this weird axiom with a fish shape. Like this is just completely alien, right? Like why would you do this? And the good news is that we extended this principle to recover a lot of known algebraic structures. And I'll say a few. We have monoids, we have semigroups, we have actually general operats. We also have heterogeneous operations, meaning, for example, a group action on a set, right? Like an action. So you have operations that are not just closed in the same set, but we have operations across different sets. And these can all be recovered in the exact same way. We have also involutions, we have anti-homomorphisms, we have basically what dagger categories are, it's general operats, as I said. It is quite successful at recovering most of the algebraic structures that people care about in modern mathematics. So my closing remarks and my final point is, well, first, there's many other algebras to explore. I'll talk about briefly this one because it's particularly important. This one, by the way, is the diagrammatic representation of the Bhattacharya-Messner product that I showed you earlier. So I'm actually going to copy that formula so just you can see briefly. Actually, I'm going to like this. You can see at a glance what I mean by this is the diagram of that. So if you labeled the indices in here, I, J, K, right? And the middle one, P. And okay, technically, label this ABC instead of XYZ, then you can see that this shape over here is basically reproducing the index properties over here, right? This is telling you that A, B, and C share, A and B are sharing I as an index and P as an index, right? But not J, right? So if you look at X and Y, that's exactly what's going on, right? They are sharing I, let's say, as an index, and P as an index over here. And then both they have two other indices, which so happen that they are shared with a third one, and P is again common to all three, right? So you can just see that the index contraction pattern of this formula is exactly captured in this hypergraph diagram, right? So this is what we called a plex diagram, and we also have functionality for that. I mean, it's a bit beyond the scope today because we don't have more time, but basically you can turn every higher arity, higher order array multiplication into a hypergraph where nodes are representing indices and the edges are representing the arrays, right? So anyway, that was just to connect to an earlier point. But when you take this, you might want to say, okay, can we find a similar situation? So let's begin with an initial state, a bit more complicated, more 9 triangles. Let's run the rewrite. So there's many, right? There's a lot of possible combinations because this thing is symmetrical. But let's see if we unlabel, if we get what we expect, which is a single output, right? A confluent single output. And sure, if you look at the pattern here, you would see that there's 3 triangles there, 3 triangles there, 3 triangles there. And all that the rewrite system is going to be doing is contracting 3 triangles into a 1 in different orders. So, and the multiple arrows is because you have the symmetry, right? You can match the same pattern in several ways because things are undirected. So indeed, you go through this and you rewrite, you get in the end that pattern, and that's your rewrite rule, and then you get a single triangle in the end, right? So it's quite a beautiful example of a confluent rewrite system. A very easy one, by the way, because this was built by hand to be literally 3 patterns of your rewrite rule next to each other, right? So you might be thinking, well, if everything is labeled, like here, like all these letters are labeling the edges, right? Just like we were labeling the edges before for the axioms. So we have an axiom, right? Because we have something that will give us many. This is, by the way, the first generation. But in the end, you have a lot of them, right? Like many different expressions, right? Which is, as you can imagine, all the ways that you can bracket 9 things with 3 brackets, right? It's many combinations. But you were thinking, okay, but if the unlabeled version is confluent, and we have all the parallels with the previous cases, so we should have a new axiom. Unfortunately, we don't. And this is where the independence comes into play. So if you were to do the check where you check for the causal dependence of the rewrites, meaning if there is edge overlapping of the applications of the rules, you would find that these are independent rewrites, right? Because, and again, that's why I meant that it was made by hand to work, because look at the initial pattern, right? The initial pattern has 3 rewrite left-hand sides of your rule put together, just joined by some vertices. So they are never going to overlap, right? All this seemingly interesting rewrite system, all it's doing is saying, which one do you want to go first, right? So this one, okay, then you have 2 remaining. Which one of those do you want to do first? And so all this rewrite system is just kind of capturing the freedom of order of your contractions. And so if you're interested in what this corresponds to in the algebra side, what it corresponds to is that if you have an operation, or a ternary operation, and you want to do 3 brackets of elements, x, y, z, for example, and u, v, w, right? If you compute this, right, which is, by the way, this should, actually, let me copy it above. So this is effectively what this diagram is capturing, right? I mean, maybe this is A, B, C, D, in alphabetical order. This is other letter, but basically you have 3 instances of a triple bracket. And what's happening is that in algebra, if you know that you have a ternary operation that you put 3 elements into, if I give you this expression, you have freedom on which order to operate, right? But the output is unique, right? Like there's a single value that evaluates to this, right? It doesn't matter if you first compute ABC and then UVW and then XYZ and then everything, or first XYZ and so on, right? Like that freedom of order of operation, which mathematicians never care about. I mean, justifiably, right? Because we know that if it's well defined, it's an operation, and therefore you can just go to the very end and get the output. That freedom of choice of order of operation, let's say execution, is captured in this rewrite system. And again, minus the multiplicity of arrows, because in that case you don't have all this symmetry. But anyway, so this is to say that the science of identifying new axioms is subtle, right? It's not just as simple as let's find a rewrite system that just is confluent, or let's find a diagram that gives me different expressions on the same hypergraph. It is more subtle than that. But the good news is that we do have the tools to probe it, because as I said, we could have predicted that this would give us a first hit for our criterion of finding a confluent rewrite system, but we would have seen that if we do the analog of this branchial graph, where we see edges when there's causal connection between the intermediate states, we would actually have seen that these intermediate states are actually separate. They are not related, because they are independent in the causal structure. So anyway, so that's just as a closing remark. And so the conjecture out of all of this, which, as I said in the beginning, we are very happy to be entering into a period of work explicitly in this direction, among other questions, but one of them being in this one, is to be able to say something about a conjecture on this, right? Because so far everything was kind of a collection of weirdness and a set of intuitions that break your brain a little bit, and then a collection of anecdotes of, hey, put these rewrite rules together and see what happens. Like, oh, look, this we get associativity with the fish, we get this semi-heap thing. It's very anecdotal. So the conjecture is formulated into a few questions, which I would say something like, first of all, can we recover all algebraic theories in this way? This is reasonable to expect to be the case, because basically all algebraic theories are expressed in terms of equational axioms, and we've seen that any equational axiom that we wanted to recover, we were able to recover, right? So there might be a question about what happens when you have several operations interacting with each other, and there, you might need to refine your labeling a little bit, but in principle, that seems very plausible. In fact, that is just part of the story to be able to recover all algebraic theories, because the fact that Zapata-Carratalá has no known equational identities tells you that universal algebra is insufficient to study that kind of object, right? Because you can define Zapata-Carratalá as a ternary product of cubic matrices, but there are many other ternary products of cubic matrices. None of them have been identified to have any equational identities. They have not been proven not to have them, but it's very likely they won't, because of the same reasons that Zapata-Carratalá doesn't. And so they are different ternary products on the same set. So they are different algebras on the same set, not just non-isomorphic, but different, right? So the fact that your algebraic theory, you know, the de facto kind of ruling understanding of algebraic theories, which is universal algebra, does not distinguish between them, should tell you that that is only part of the story, right? Like universal algebra is not gonna go all the way to cover all these cases. And so one of the hopes of this methodology is that we not only recover all algebraic theories, but in fact have a working knowledge of things that are sort of invisible to conventional algebraic theory. Okay, so that's one thing. The other, and more to the conjecture itself, is for a given axiom, it turns out that several hypergraph rewrite systems are able to recover it. The fish, for example, the axiom of the fish, the semi-heap axiom, you can recover with the fish, or in fact with any size of hypergraph edge that fits the same shape. So the fish was two vertices into a one vertex to make a triangle, into two vertices, into one vertex, into two vertices, right? It was 2 into 1, 2 into 1, 2 into 1. If you do m vertices into n vertices, that still works, right? And so you have infinitely many hypergraph rewrite systems that all capture the same semi-heap axiom. So the question is there a well-defined notion of equivalence that would make the correspondence unique, right? So you want to bundle up a bunch of hypergraph rules and initial states and what we call rewrite systems as a collection, and make them all bound by the fact that they recover the same algebraic axiom, right? And then, of course, in the end is what unknown mathematical structures are waiting to be discovered in the computational universe. And this was my original motivation, that connecting all the way back to the Lie algebra story that I told you 2 hours ago, the reason why I got into this funny business of doing weird pictures and looking into these alien looking structures is that, remember, there was no known candidate for what would be the exponential of a 3 Lie algebra, right? And this sounds like a very technical term, but basically what that's telling you is that there was a missing gap in mathematical creativity by humans, right? Like humans had not developed a mathematical device that could fit the whole of your problem, right? Like the problem of your machine had a shape that, you needed a cog that was nowhere to be found. And so I got into this business thinking of several things, but at one point I realized, wait, this is a real opportunity to dig up unknown mathematical structures with a very systematic and powerful system. So now, the question still remains. There are no, hard results yet, but now we have a fairly confident system to use, which is this whole business of define your rewrite system, see if it's confluent, see if it's causally dependent, has this kind of dependencies between the intermediate states and so on. And if we get positive results, and because, by the way, these are all discrete, we can enumerate all of them, right? By increasing size, we can exhaustively cover every possibility, right? Up to any given size. So we can start to have definitive answers. We can start to say, up to this size, which would be completely unfeasible for humans to do beyond, because you would have to write things down as a mathematician. So you can probably cap everything at size 9 or so. Like if you have to write 9 terms in a single expression, there's no chance that your brain, I mean, unless you're a super genius, you're going to do algebra with that, right? And if you have to explain to other humans, it's hopeless, because you have to write in a blackboard or something, and it's just completely hopeless. So we can make some very concrete claims that for any humanly looking mathematics up to a certain size, we can be sure what are all the possible structures that would exist that have these properties, and therefore we can settle some questions about hierarchy structures in this way. So yeah, it's a very promising feature, and I'm very glad that we had some time to discuss it. So yeah, thank you very much.
Thank you, Carlos. Let's thank the speaker, and we could take a few questions.
Yeah, I'm all ears.
Can I ask a quick question about the Lie stuff? So it's so interesting to me to think about like Lie algebra in terms of a binary. I never really thought of it that way. I think of like it's like a group of transformations or something. So I guess maybe you could say, in what sense is it a binary? In the sense that the 3 is a trinary? Is it just that it takes in an input of one type and then spits out an output of the same type, or what is it exactly?
Right. So the Lie algebra is a
Just a
binary
matrix.
because it's because it's the bracket, is the Lie bracket. So
Okay,
for if you're thinking in terms of transformations, that would be the commutator of transformations, right? So I mean, I jumped directly to talk about a Lie bracket, which is the commutator of transformations, right?
Okay.
But that's it. That's in the sense in which the Lie algebra is binary.
So let me follow up with that. So what is binary about these kinds of transformations? I mean what, I guess I know that there is a bracket, and I know that it's like used all the time, but I'm not sure like why the binary, I guess, is the question.
Right. So the binary, by the way, so there's two layers to your question, both interesting. One very simple, the other complicated. So I'll answer the simple one first. So the binary term that I'm using, I am referring to the arity of the operation of the bracket. So it's just an integer, right? It's just to say that you need 2 arguments to fit it into a commutator for it to make sense, right? So that's very uninteresting. That's just simple. Now, there's another layer to your question, which is, what is binary about a transformation, right? What is binary about something that transform a set of things or a space or something, which connects to the question that Nick was mentioning earlier. There is something binary in the same sense that there is something binary about a directed edge in a graph, right? When you represent a map or a transformation, you typically, diagrammatically, you have your vector space V and you have your vector space W. It's a linear map phi between V and W. You write as an arrow from V to W, right? So the binarity in the transformation is in the cardinality of sets involved in the transformation itself, right? So it is not quite the same. So I wanted to distinguish it very clearly, because it's not quite the same as the arity of operations, because arity is sometimes equated to the number of inputs in your operations. So there's nothing. I mean, an algebraic operation is nothing but a map from 2 arguments, so 2 copies of your space into some other space. So you could still write it as you put a circle around the 2 copies of your space, and you put an arrow from that into another space, right? So in that sense, you say, wait, but so what if I have 5 arguments and I just have a single output? That's still binary in the sense that it's input output. So that's why I distinguish normally when I talk about arity, I usually refer to the number of arguments involved in a simultaneous operation, right? And simultaneous means that you're doing operations one at a time, right? If you want to distinguish a sequence of operations, then you would make it explicit. But if you don't want to distinguish sequence of operations, then the number of elements involved in a non-sequential stage of operation, that's arity for me. If it's sequential, then and by the way, the example that I brought up in the end is a good illustration of that, because if we want to parse this expression mathematically, that expression over there is single value. There's no causality, right? There's no sequence, because it's just, you know that if you have an operation, you can sort of nest it as many times as you like, and you would just increase the number of arguments, but everything is well-defined and single valued, so things will just become, well-defined, single valued all the time. However, if you want to compute this, maybe with an actual computer, a computer algebra system, or these are numerically valued and you feed it to some calculator or whatever, or you are very fancy and you want to represent it as a hypergraph and then compute it with some rewrite rules, then your sequence actually matters a lot, right? And if that is mathematically like a single line, becomes computationally this complicated diagram over here, right? Obviously, you can have theoretical predictions and theoretical bounds of what is to happen. So you don't need to actually go through all the possible diagram, and you apply your usual normal form theorems and so on. It's like, okay, so I don't have to compute all paths of the calculation. It's enough to find one, and that should be equal to all the others, right? But it's an important question that you're raising, that the arity, there is a notion that is kind of simultaneous and kind of space-like, almost, I would like to say, right? That is kind of at this moment we are doing an operation, and there's another aspect which has to do with sequentiality and sort of the temporal dependence of things.
I see. Interesting. Okay, that helps a lot, actually. Thank you. Yeah. Yeah, I brought up a comment about tensor networks in the chat, and I guess there's like several multi-arity examples there where you'd have taken multiple objects in the space-like sense, so to speak, and then you would return like a vector or something like that. So I thought that was an intriguing application potentially for this.
Yeah, so I mean, tensor networks are very morally close to, or conceptually close to all this business. My understanding of the classic literature on tensor networks is that when they use the term tensor, and perhaps this is a moment for me to expand a little bit on my kind of caution not to use terms like tensor and so on early on. Tensors are objects that have been inherited mostly from mathematical physics, and that is to say that mathematically speaking, they are multilinear objects. So typically they are, many input, many output multilinear objects, right? So in a way, tensors are kind of a higher-arity generalization of linear maps, right? So something that is well-defined on vector spaces, and that you can mix and match in all ways that you like in programming, right? Like you have all these functions, and you could have two outputs of this one go into the two first outputs of that one, and then it takes also the three outputs from that one. You have this sort of if people have seen monoidal categories, this is kind of the language of that, right? With your stream diagrams and all this kind of stuff. That is the language of tensors as we know them, right? Like the mathematically accurate tensors. Now, in the whole field of machine learning, for example, people talk about tensors all the time, right? In that field, that's not what tensor means. In that field, what tensor means is array. It's really just an array. And in fact, sometimes they, what is it called again? Ragged tensors. They use this idea of ragged tensor, which is basically just like a tensor or an array that can have an equal length of like sub lists or sub arrays. So those things are natural in that context. And this is a very meta commentary that I'm going to make here, but we are living in a moment where these two things are each fully justified and powerful and meaningful, but there is a fair amount of confusion going on. I mean, not confusion in the sense that people are doing things wrong necessarily, but confusion in the sense that we are obscuring part of the conceptual content of our models or our understanding, because people just think that when you see a high order array, like a multi-index array, they just think, okay, this is a tensor, and because you have piles and piles and piles of textbooks on tensors, then that's where you should find all your mathematical technology. That is the problem, right? That all these illustrations that I like to do with at the beginning, I spend a fair amount of time sort of going over these examples, because these are totally pedestrian. Like an undergrad would understand them, and even people in high school could understand these sort of things. I mean, I remember when I was in high school, I found a notebook the other day that had, when they explained to me dot products and so on, I remember, thinking, all right, so matrix multiplication is like rows and columns, and then, but so a vector is a row and a matrix is a table, and then I had like this cube drawn in my notebook from when I was whatever 15 or 16, and then with rows it said dot product, and with squares it said matrix multiplication, and then with cubes I was like question mark, like all the way back then. So I mean, I was not doing anything fancy. I was just like learning it for the first time in school and thinking, hey, what do you do with these things when you go higher? And it turns out that it's a big mess over there. Like it's not obvious at all what you do. The theory foundationally for it is not well developed. And part of the impediment to having well-developed theory for this is precisely the fact that when you say tensor, half of the world means array, and the other half means multilinear, multi-valued linear map, right? So those things coincide when you choose a basis and so on in some strict categories, but they are absolutely not equivalent, because and if someone wants to have one takeaway, if you ever want to be in at a party where there's computer scientists and physicists and mathematicians, you can use this as a party trick. Basically, when they tell you, no, but come on, every tensor has an array expression, right? You can just write in some indices, and that's it, right? That's your tensor. Then you should have a comeback that says, well, technically speaking, every tensor has infinitely many matrix representations corresponding to all the possible basis changes of your space, right? So then the comeback is like, so okay, fair enough. We're gonna go down the route that all tensors are actually matrices in some sense, but then you need to supply this extra information of what are all the matrices that correspond to your tensor, which is the same thing as to say, what are the transformation properties that you want out of these arrays. And then that's where the divide between the computer scientist and the physicist will appear. Like you would be able to basically split the Red Sea in the party between physicists and the computer scientists with this question. I mean, and again, not to make fun of anyone in particular, because it's not that there's a problem or an error in any of the sides. It's simply that in computer science, or specifically deep learning and so on, arrays are the end of the story data structure that you want to work with. This is the true foundational base reality of your mathematics, the arrays themselves. In physics and differential geometry and all the mathematics that developed for physics, you've built everything on top of the idea of equivariance and invariance, right? You've built and covariance, right? You've built everything on top of the idea that a particular coordinate expression is just convenient, but you can change it, and all the relevant information will be preserved, right? And so specifically in linear algebra, this means that objects are only well defined when they are defined up to arbitrary base changes, which is to say arbitrary invertible linear transformations, right? So in the array side, in the computer science side, those notions are not well described, right? Like the people are not talking about what are the possible transformations that you can do to your array so that it doesn't change. I mean, except for permutations. I mean, everyone understands that if you permute everything, you can reverse the permutation, and that's easy. But like more sophisticated transformations intrinsically, people are not talking about that typically, right? In computer science, I mean, there's some conversation, but it's not the same level of it's like a standard, right? In physics, you don't talk about things that are coordinate independent, because it turns out that actually they lack reality. for it, right? Like if you find something that's coordinate independent, you would actually go into reality and you will fail to reproduce your experiments, right? So, but in computer science, that's not the case, because these machines are built on these data structures, and so that's the kind of ground truth in that field. So anyway, it's a very interesting time where these things, because the mathematics, the basic mathematics and theory for this is kind of in early stages. We don't have a good general theory of arrays that you just pull out of a textbook and just are able to navigate your deep learning architectures just like a breeze.
Like my view why computer science lacks what actually lacks computer science in terms of tensors. It's just the way they do it. They always forget that it's a vector space, so they always deal with components. But as soon as the data structure also incorporates the basis, the notion of basis in some way. So like, for example, I like to my objects have a basis already, like in the quantum framework, all my objects have basis intrinsically, so I know how they transform. But computer science also care about one half of the problem, only the components, right? The basis is always implicit, and as soon as you incorporate the notion of basis into your data structures, your transformations and even the generalization of components, would make much more sense.
Yeah.
Even your components can be generalized. It doesn't have to be necessarily be numbers. They can be the vectors themselves, like whatever elements of the algebra can become the components, or even operators. And so again, these objects, when they also know about which basis they represented, it's actually much more powerful than just if you talk about the components individually.
Yeah. No, and so that's definitely one direction in which this is fixed by introducing data structures that know about basis and so on. But my take on this is a little bit complementary to what Nick just said, which is that I think there is a lot of uncharted territory beyond known linear theory or even differential geometry as we know it, right? In this concept of coordinates and covariance and so on. And you were alluding to it when you said maybe this is a generalization of angle and you need to have some generalization of what it means to be contravariant and covariant and things like that. I think that is to be defined. And actually, funnily enough, because the computer science side of the question, they don't care about the basis most of the time. There's more ground over there to discover the usefulness of these structures potentially, and it's if you can use them for something useful, quote unquote, or like for example, I've been working with some deep learning models, and we've been trying to look at what changes you can make in the architecture to introduce some of these higher-arity notions, like higher-arity dot products or like hypergraph encodings of some things, and it's very very basic experiments of like, what if you change that? How does that affect the training performance, or how does some basic questions like that. So to me, if you find some usefulness in some realms, in more computer sciencey areas, it's easier to then kind of motivate and push the mathematics on the more theoretical side to incorporate those as something useful. Because as I said, tensor networks and all this quantum physics, quantum computing kind of frameworks, they are very firmly based on multilinear theory. This has worked extremely well, and to this day, we don't have good reason to say, we have to kind of like do away with it or modify it fundamentally. And it works fantastically well, right? But when you're not dealing with a world of like qubits and like measurement processes and the coherence and so on, you might want other kinds of mathematical objects that are not like your monoidal dagger categories as people use in quantum mechanics.
All right. With that, I think we should end, and let's thank Carlos once again. Thank you, Carlos, for this excellent and inspiring talk. The recording will be made available, in maybe a day or two. In the meanwhile, let's catch up with our mentors and We look forward to Group B project meetings later today. For Group A, the day is free, but do catch up with your mentors, discuss your projects, and so on. Have a good rest of the day. Bye.
Thank you, everyone. See you
Thank
soon.
you.
Thank you.
Appreciate it.